just want to talk about what we're talking about here. What is an alloy, and why are we talking about crystal lattice structures, okay? And how does it connect to our redox? Everything, okay? Because how oxygen can attack a metal in its crystalline structure can affect how well an atom loses electrons. We already saw that aluminum, although it's highly reactive, actually makes a passive layer. It's called passivity, where the salt of that layer can actually prevent any more oxidation. So the first step, and the reason that I'm doing these types of calculations, I don't want you to ever forget how important it is to think about the structure. The structure of our metal, the structure of our salt, now those are differences, okay, affect its properties, all right, either in oxidation or preventing oxidation, because as we're going to learn, salt layers do not allow conductivity to occur as well, all right? So if you ever had a rusted, or if you ever had a battery that's in a flashlight and you saw some corrosion, one thing you do is you can just take a wire brush and clean off that corrosion, and the connectivity or the conductivity will appear if there's some spontaneous reaction still left in that battery. Okay, oxides don't, or salts, I should say, do not conduct electricity as well. We'll talk about that. But let's start with NaCl. This, of course, is a lie. Unbelievable lie. You look at that and say, oh, it's a sodium and a chlorine bonded. Wrong. What it really is a positive ion who is smaller because it lost an electron, which means the protons are outnumbering electrons and pull them in, is attracting a chloride ion, which, by the way, is now bigger because it gained an electron. The whole thing is made of charges. We don't write the charges because the whole thing is electrically neutral. But it's still a lie because it doesn't exist this way. How does it exist? Well, this positive attracts another negative, and this attracts a positive, and the beat goes on. It continues out until, I don't know, the crystal stops. We don't say NaCl is 1,000 sodiums and 1,000 chlorines after we look under electron microscope. We just know it's a 1-to-1 ratio. That's an empirical formula. You have to make a leap. Now, this is called a salt, which, by the way, is an example of an ionic compound. And you think about it, it's made of ions. Ions stick together coulombically so strong they're solids. And in this case, it's a simple cubic structure. Simple cube. Okay, it's a 1-to-1 positive to negative. I've been using this all year as a great example. Okay, the little blue guys here are my smaller sodium metals who lost electrons. We know they start out bigger. Now, what's the deal? Well, this crystalline structure continues on and on and on, okay? And so you have to understand that we're dealing with the ratio. We call it a formula, all right? And of course, how strong they interact affects how well they dissolve in water, so forth. But we're gonna find out today, they're not always gonna be simple cubic structure. Their structure can also affect how well they can coat or not coat a metallic structure. So here's an important solid. Anytime you've got a non-metal, small atom, above the staircase, hooked up with a metal, below those staircases, there's gonna be an ionic reaction. What just happened? The sodium gives electrons to the chlorine, and of course, that's how it's occurred. Now, there's also a metallic substance. Okay, let's talk about iron. Solid. That seems to be a lie too. When I write iron solid, do I have one atom? No. The iron is going to exist in some kind of, I'll make it face-centered here. You never have to know, but here's iron. It's in some arrangement, repeating structure. And it sticks together by metallic bonds. We call this a metallic compound, okay? Metallic, and we'll talk about that. But they both are solids, which means they both have crystalline structures. And they both are related because, well, they're the result of something very similar. I consider salt, or all salts, which are ionic, positive and negatives, which you should be able to identify, okay, is nothing more than the rust of what? Metals. Now, people don't like to use that word. Rust is usually for corrosion. Metals do what? They lose electrons. They become positive. The substance that gain electrons, most of the time it's oxygen, in the case here it's chlorine, they become negative and they stick together. And the properties of the salt, which is the result of the oxidation, are far different than the pure metal. Sodium's a solid metal, and this crystalline structure is far different. Sodium, as I'm going to show you, is a silver metal, conducts electricity. This doesn't. It's a white solid. Okay, there's different properties here. So I think of the ionic compounds are the result of the oxidation. Case in point, okay? If I have oxygen, we'll put oxygen on this end, O2. What's it going to do in the presence of iron? Well, it's going to pull electrons for reasons we've explained. And electrons are pulled from the metals. Metals lose electrons. What's going to happen to iron? Well, it's going to become +3 or +2. Oxygen becomes -2. And guess what you're going to make? You're going to make Fe2O3. Now, why do I draw that? Well, I know that iron, in its most stable form, is going to become +3. It's going to lose enough electrons to get its most stable oxidized form. It's going to lose 3 electrons. Oxygen, though, is going to gain 2. And if you notice, I crisscrossed. 2 here, 3 here. I don't need the charges anymore. But that's, guess what? That's a salt. That's the result. That's the rust. So anytime we talk about corrosion, rust, or salts, that is the product of the ionic reaction between something that's really good at oxidizing or being an oxidizing agent and someone being a good reducing agent, or a metal good at losing and a spontaneous process. Everything in this right here is tied to what we're doing. Okay? Now, we know that from your experience, if I've got iron rusting, especially in an old car, okay? We always had old cars in my dad's, and my dad had these junkers, and one of the favorite things to do was put my finger through the fenders when they were just like, there's just like so much rust. You could put your finger through, and you hated when I do that. But the reason is, iron, when it oxidizes and becomes iron 3 oxide, its three-dimensional shape isn't simple cubic. In fact, it's far different from this structure here. In fact, what it does, it's very interesting, I think it's really cool to think about. When it makes an oxide, let's make this Fe plus, so it's going to make this oxygen -2. Okay, this becomes +3, but interesting enough, this O -2 pulls this +3 into this pattern. These two negatives will pull this +3 into a different structure by which the iron was. And so if you notice, we're creating the rust, the iron oxide, but look what we're doing. By pulling the iron into a different three-dimensional structure, you're exposing more of the iron to what? Oxygen. And it's going to do what? Pull the iron here into this crystal pattern. And it keeps exposing it until all the iron is gone, converted to a very flaky, okay, weak compound as compared to the pure metal. And that's how it works. Now, if I've got pure aluminum, okay, and again, here's pure aluminum, and I'm also going to just put it into a body-centered, okay, it could be face-centered, and again, it's not important, but there is my metallic crystal of aluminum. Now, when it reacts with oxygen and pulls electrons, what do we make? Well, we know aluminum becomes +3, oxygen becomes -2. We crisscross our charges and we get aluminum oxide. Again, this is iron ore, another fancy word for the rust or the what? Products of the redox reaction, or aluminum ore, or aluminum oxide. This is what we find in the ground, obviously, but these are both solids. Interesting enough, aluminum oxide has very, very, very similar three-dimensional patterns as the crystal. So it makes aluminum oxide, this becomes, let's say, +3, and this becomes -2, -2, and essentially what we do is we make an O-2 layer, okay, on the aluminum +3, and because the pattern of the metal matches the pattern of the ionic compound that results after oxidation, this coats the aluminum. We call that passivity. And that means that once the oxide layer coats the outside, there is no more aluminum exposed. Okay, and you probably know like aluminum that's outside kind of get crusty yellow. Okay, and so this, once it reacts, doesn't expose any more aluminum, unlike iron oxide, which has an entirely different three-dimensional structure. So knowing the structure and the structure of the resulting compound can affect the ability to keep oxidizing or not. The problem in your STEM lab, your voltaic cell 2, is that you picked aluminum, so did I, with great reducing ability or ability to oxidize, right? It was way over 1 volt, but it was so reactive with the water, the reason why the voltage stopped really quickly is it made an oxide layer. I added hydroxides to actually dissolve that to keep exposing the aluminum. Of course, you guys didn't know that, all right? But it's important to realize that, okay? The structures these guys make as the result of the redox can affect the further oxidation or prevent the oxidation. Okay, last night or this weekend we talked about an alloy. Now what's an alloy? An alloy is where we actually kind of put or dope is a word we use in chemistry to change the atoms in a crystal. So if I go back to my iron layer, forget the iron oxide, and put my irons back. Okay, so here is metallic iron. What they do for stainless steel is they add some chromiums. Okay? And they don't have to add a lot, but just enough chromiums, okay? Especially on the outside layer, to do what? Well, what chromium does, it reacts with oxygen. It makes chromium oxide, which is, again, another salt. But that salt, just like aluminum oxide, and unlike iron oxide, is able to match, okay? So this becomes +3, and then we have what? O-2s and O-2s on the ions. The bottom line is we have an oxide layer that can coat the iron. Chromium 3 oxide has a different three-dimensional shape that matches the structure of the iron. Really cool. In a way that the iron cannot be exposed anymore to oxygen and therefore prevents the rusting. Stainless steel is stainless because essentially the iron cannot oxidize once the chromium rusts. But what's cool about the chromium rust is that because it's such a thin layer, atom's thin. We can't see it. So really stainless steel has rusted, except the chromium oxide rust is see-through. It's too thin. But it's thin enough to what? Create a layer and a barrier to more oxygen reacting with the iron to make iron oxide. It doesn't last forever. Sometimes that layer wears off and eventually stainless steel will expose the iron, okay? But again, what did we just do? We replaced one atom here, and that atom, by mixing it a certain way, making an alloy, okay, creates and changes the properties. So why do we use alloys? We use alloys to take metals and increase their chemical reactivity or decrease them, make them corrosion resistant or not, increase their chemical conductivity, become a better conductor, a lot of times to make them more malleable, to give them more strength, all the above. And it's called metallurgy. It's a huge, huge, huge science where we mix metals all the time to see the properties, and it becomes very, very advanced, okay? Back in history, it wasn't so advanced. They took the earlier swords, okay, were the soft metals. Lead, copper, these are soft metals. They had low melting points, and they're very malleable, but when you hit a sword of copper on lead, they bent, they broke, okay? Someone got smart and said, what if we mix some tin with copper? All of a sudden, that thing got harder. That's called the Bronze Age. And then about 3,000 years later, someone was taking iron, which is harder to get, so you had to be a little more advanced, and where they were melting it, they were burning, okay, carbon-based fire. They were using logs, right? They were burning wood. Wood is made of carbon. So the carbon was getting into the metal that they were what? Into the iron. And what does carbon do? Well, if we replace my iron here by putting the carbon, okay, in here, which we know is a smaller compound, what's it do? Well, and these are little C's. And let me just do this drawing a little bit better. So what we made is the Iron Age, but really we were making steel, and they got better at it. So let me just draw this again. You just make sure you understand. So we got the salt, get rid of that guy, and let's draw this a different way. So let's say I have Fe atoms, iron. By the way, the Latin word ferrous, okay? And the beat goes on. So what they did by accident, by melting the iron and having some carbon, okay, and the carbon did what? It found its way into these little areas. Now, by having the carbon, which we know is smaller, if you take a blast of some kind of force, having these little atoms here, okay, are going to prevent this iron from sliding over and breaking. And that's where the carbon increases the strength of the iron, and that's, of course, what we call it steel. Iron by itself isn't strong enough. But if you add what we call coke to the smelting process of making iron ore, iron oxide into iron, we make steel. And steel drove the Industrial Revolution besides the steam engine. Having steel gave you the ability to make skyscrapers. The Empire State Building, built around 1900s, only worked because we were able to figure out how to produce tremendous amount of steel. Think of locomotives and how heavy a steam engine that size to pull people across the United States. They couldn't sit on wood. You couldn't use wood platforms. You had to have steel. You had to have strong steel support a 10 or 12 ton locomotive. All right. So it's the steel that we figured out that drove the Industrial Revolution and the expansion of the United States. And here it is in chemistry. Okay, it's amazing. But this is called not a substitutional, but an interstitial. Okay, it's inter, and it increased the strength of the iron. All right, so let's go through a couple of more alloys and we'll get to the homework. Okay, so I want to go through here. We'll talk about superficial anodes. All right, so here's iron oxide. In iron oxide, you can see how it pits up in the crystalline salt. So to create this strong angle, we have that iron pulling up, and that's the area where we'll make a pit for where the iron was. The iron ion is going to get pulled into this structure upward and exposes what? More of the iron. That's why when we have iron rusting, it can keep going through. This salt structure is far different than the structure of pure iron. Okay? All right, so moving on. Stainless steel. And here is chromium and iron. This is the stainless steel mixture, not the steel here, but this is stainless steel. And notice they're both what? Have to be gained electrically. We find these guys in nature this way. We have to force them to become metals. Okay, that's why we use electrolysis to make this happen. But when we mix chromium with iron, because the what? The size of the atoms are similar, okay, it keeps the structure stable. And that's what's called a substitutional alloy. Now, why is that important? Well, if this thing is too big, okay, it's going to push other atoms outward if it tries to get into the crystal. And when you push atoms outward, what do we know about Coulomb's law? Q1, Q2 over distance squared. The distance of the other atoms in the crystal become big. which does what to the force of attraction? And it destabilizes the crystal. The crystal's going to break apart. It's not going to stay that way. So you have to make sure that when you substitute one for the other, they have to be of similar size. It's that easy, okay? So anytime you're identifying for the AP a substitutional alloy, obviously, okay, it's got to be the same, approximately the same size. And to know it's not, it's going to be very obvious, okay? Here's an example of chromium 3 oxide. It kind of matches iron, okay? So chromium oxide, when it's chrome, gives you that passivity, that coating effect when you make the salt of the redox reaction. And I'm not going to play these, but you can, if you play these side by side, you can see that. Well, I will. I'll try. So here's chromium 3 oxide. I remember that. There's that, and the iron 3 oxide. You can see this pit here that this one doesn't have. But in any case, moving on. Okay, we talked about the bronze and iron steel. Brass is a very important alloy that we see around. And what mixing zinc with copper does, it gives the zinc a little more resistivity, or even the copper. So it's corrosion resistant. It looks like gold. So people like to use it for ornamental things. It has antimicrobial properties. Anything with copper has antimicrobial properties. It lowers electrical conductivity, so if you don't want it to conduct and you want some sort of an insulator, it does that. Lowers the coefficient of friction, makes it have less friction. Think about sliding metals together in an instrument. But the biggest thing they use the brass for, because it looks nice, is that it's actually very malleable. It's more malleable with the zinc, meaning you can shape these ornate structures in musical instruments. Some people say that it sounds better with brass, but they gotta get the brass out of here. Okay, now, so zinc and copper have about the same size, so it's a substitutional alloy, okay? And that being said, we're gonna move on, moving forward. And notice that they're found together. They have similar outermost electrons. We'll talk about them. You say, well, why do they have the same size? Well, zinc has one more proton, so you would think it's going to be smaller, but then it has one more electron, so they kind of balance off there. We'll talk more about those things later in the course. Okay? So, I want to do a problem. Oh, I want to talk about a problem we had for homework. Okay. Oh, cancel. And it's the calculations. Was it this one? So I want to talk about your homework a little bit. And that's not the homework. Right? Is that the homework? No. You can speak up, guys. No, thank you. That's the homework. Okay. So, talking about the homework real fast. Done. Okay. Talking about the homework, this was a problem that we did in class. The only little difference here is that I used nanometers. So nanometers and picometers. Nanometer is 1 × 10 to the 9, which means you need a billion of them to make 1 meter. We used picometers last week when you guys were home, and of course that's a trillionth of a meter. 1 × 10 to the 12 of them equals 1 meter. I will give you both of them in a quiz or test. It's not about memorizing them. So where I start from a nano or pico, they're small units that we use for, of course, very small things like atoms. So this was a repeat question, except I used nanometer. We're going to skip number 2, but I want to go to number 3. There's an important calculation here. I say hint, hint. Okay? Now, I'm never, ever on a test, okay, going to make you memorize what metals have face-centered or body-centered. I'll give you always the what? The unit cell. I expect you to recognize that that is body-centered. And I expect you to know that that has how many atoms in it? 2. Face-centered has 4. I think that we can figure that out. That part, I'm expecting to make a leap. But here's a question. It's really important to me. Calculate the gram atomic mass. Think about this for a second. All right? If I get the lattice constant from X-ray crystallography, right, by shooting light, and we get the scattering effect and measuring the distances and knowing the type of light and the angle at which it hits the metal, I can get this what? I can get this important dimension, which is of course a cube, right? And I'm telling you it's iron, but what if you were trying to identify what this chemical was? You could do so by density or by a gram atomic mass. Any case, I'm telling you it's iron, it's body-centered, I'm giving you the lattice constant, I'm giving you the density, okay? Notice I'm giving you in kilograms per meter squared. That's what lab today is about, dealing with this, and this is what's weird, okay? And it's a great way to think about why you can't do picometers squared to centimeters squared. You can figure that out, but it's really, really complex. I've been telling you guys, hey, go to centimeters first and then cube it. Don't do the conversion, and I'll explain why. Let's go through this problem, at least we walk you through it. Okay, first off, they want the gram atomic mass. What is what? They want the mass per 1 mole of atom, correct? Okay, well, can't we solve the mass of 2 atoms? Divide by 2 gives you the mass of an atom. To get the mass of a mole, take that 1 and times it by the actual number of a mole. That's how I'm going to do it. Okay? All right, now, how do I get mass? Well, what do I do last? They're giving me density. They want mass. I know I can get the volume, my lattice constant, right? So I'm going to solve for mass. What's mass? Mass is density times volume. Yes?
On the test, will we get like mass equals density times volume?
No. I expect you to know what density is, and I expect you to manipulate this algebraically. D over 1, solve for M. Yeah, I don't think you, honestly, I think density is in your reference tables. I think you have that formula, so you should be able to solve for mass. Okay? And don't give me the triangle thing. I lose points. I don't want to see the triangle. You can learn in science. I do not accept that. Okay? D equals M over B, right? Mass over volume. Solve for mass algebraically. Times this side by what? Volume over 1, volume over 1. Okay? Mass is density times volume. Okay? Manipulating equation is all part of this course. Okay. So there's my plan. Got to get a density. But wait a minute. I want grams. Okay? I'm in kilograms per meter squared. So that's my density unit. I want to convert my density unit into grams per centimeter cubed. Why? Well, think with me, party people. If I have grams per centimeter cubed, and right here, density is going to be grams per centimeter cubed, and I times it by a volume that is what? Centimeter cubed. What is it going to give me? Grams. Okay? So, here's what I do, party people. I write down the density, kilogram per meter squared. I'm going to get rid of kilograms, because I want grams. So I know there's 1,000 grams. Kilo means 1,000. Get rid of kilogram. There's my 1,000. Okay. But what is the conversion between a meter cubed and centimeters cubed? And this is something that is not easy to understand. It's not a straight conversion. So let me help you. In my hand I have a liter. This is a liter. In this liter, if you can't see, there's one little cube missing. That is a centimeter cubed. Centimeter by centimeter by centimeter. A centimeter cubed is actually the volume of a milliliter. That's important. So, this is a liter. Why? Because this is 1,000 centimeters cubed. 1,000 milliliters is a liter. And how does that work? Well, I have what? 10 centimeters by 10 centimeters by 10 centimeters. What's 10 times 10 times 10? Length times width times height. 1,000 centimeters cubed. You with me? Good. Now, we want centimeters cubed. How many centimeters cubed is in a meter cubed? Whoa, meter cubed. A cube meter is what? Okay, a meter high. A meter wide. Okay, and a meter this way. Length. So I've got a cube. Now wait a minute. Centimeters, meters. Whoa, isn't there 100 centimeters? How tall? So how many of these would be tall in my centimeters? Would I need 10 of these? So I have 10 of these liters, or this is called 10 of these, right? So I have 10 of these this way. I'm sorry, 10 of these this way, 10 of these this way, and then at you, 10 of these this way. What's 10 times 10 times 10? 1,000. So I have 1,000 of these. If I was to stack 1,000 of these, 10 wide, 10 high, 10 long, that'd be a meter cubed, correct? Right? 1,000 of these. That's crazy, right? It's pretty big. Okay, wait a minute. So we have 1,000 of these, but how many centimeter cubes are in here? 1,000. So 1,000 times 1,000 is 1,000,000. In 1 meter cubed, there is 1,000,000 centimeters cubed. That makes sense? Hard to understand that without understanding the volume relatives here. Can you see why a nanometer cubed is going to be very difficult to convert to a centimeter cubed? Right, that's why, so when you ever want to go to centimeters cubed, go to centimeters first. So that's important conversion. So I get rid of cube meters, and now I've got grams per centimeter. That's an important conversion. We're going to practice that in lab today. Good. Now what's that? What's that equal to? That's my density now. I've got that in grams per centimeter. Now I need volume. Hey, use the lattice constant. Okay, where's my lattice constant? I gave it to you, okay? And it was, of course, determined by X-ray crystallography, Bragg's law, okay? Things that we talked about, the scattering. And there it is in nanometers, okay? Convert to centimeters before you cube it, because that's what? Length times width times height. So that's what I do here. Take my nanometers, and I know that a nanometer is a billionth of a meter. So there's a lot of them. Hey, big unit, small number. Small number, big unit. Nanometers cancel. I got meters, and I convert to centimeters. Some people can go right to it. Okay, it's fine. So I get 2.87 times 10 to the negative 8 centimeters, but I want a volume. So I'm going to cube that. And when I cube that, that's my volume. Okay. So, what do? I have, so mass is equal to density times volume. Got my density in grams per centimeters cubed. I got my volume in centimeters cubed. Centimeter cubes cancel. Put this in my handy dandy calculator. And I get 1.86 times 10 negative 2, of course, grams, because everything goes. But this would be the grams of 2 atoms in a what? Body center. Divide by 2, and now I have the mass, going to be small, of 1 atom. All right? But what was the question? Then with the gram atomic mass, the mass of 1 mole. Well, I have the mass of 1. Okay, what if I wanted the mass of a dozen eggs and I have the mass of 1? Times it by 12, right? Well, a mole is like a dozen and it represents a number. That number is huge. Of course, I times it by what the mole represents. And now I get the gram atomic mass of iron. Okay? So we will practice some of the pieces of that. That was the most important thing I wanted you to get from last night. Now, also from last night, this is a typical AP problem. You don't have to memorize stainless steel is chromium and iron in a substitutional alloy. You don't have to memorize that chromium is going to make some passivity when it reacts with oxygen. They tell you all of that in these problems. I'm trying to teach you to make sense that you understand why we study structures like this, why we study the three-dimensional structures, because it affects how they oxidize. So what they're saying is they say all of that here. And look what they give you, party people. They give you the atomic radii. They have iron and chromium alloyed together. Oh, they've got similar what? Atomic radius. So they're going to replace each other. Okay? Look at carbon. Oh, very small. Oxygen, very small. So, when you talk about all of that, the only answer that makes any sense that if you have this oxide layer, remember, look at the question, look how they present it. You're looking from the surface. Look from the surface, there's your oxide layer. The chromiums make an oxide layer that are a few atoms thick that don't expose, right? It fits right in the crystal. You have a little bit of carbon. Why a little bit? Because, and a little bit here, okay, because not 100% carbon's mixed. And on the inside, Okay, on the inside, how come you don't see any oxygens? Because the oxide layer is where? On the outside. It's just that simple. Some of these choices are ridiculous. Look where chromium is. They're saying chromium's smaller than iron. Come on. Okay, they give you the sizes. Okay, and then they have what? That one could be okay, but then here's inside. You're not going to have oxygens. Okay, so an easy problem, and it shows you what you have to know. Isn't all these details, just the basics. Okay. All right, now, this question, okay, a lot to do here. I want to kind of go over that question by the question number 3 in that worksheet that we did, in class when you guys were live streaming. So I'm going to take that out. So that's this one. Yeah, that one, but I don't want the key. Calculations. Okay, number 3, I want to do together. And that'll be the last piece. And this is also tied to lab. And here we go. Okay, so in this problem, got gold, aurum, and they want you to calculate the lattice constant. So they want you to get this dimension, which we normally get from crystallography. They want to get that value. What'd they give you? They got the atomic radius. Okay? And that's it. Okay, well, if X-ray crystallography gives you a spread, gives you a diffraction of light that hits that metal a certain way, we know if it's body-centered or face-centered. Is this face-centered or body-centered? Face-centered. Now, there's something really fun about the face-centered. Okay? To get the lattice constant, you can't really use the atomic what? Radii here because there's a gap. But where is there not a gap between atoms in face-centered? Right across the hypotenuse. Here's a radii. Here's a radii. Here's a radius, I should say, a radius. This entire length here is 4r, 4 times the radii. And then if you make this dimension here happen, you can see something that kind of happens here. We got a right triangle, and we have a 45-degree angle, and a 45-degree angle. By knowing the atomic radii, a radius, timesing it by 4, I've got my hypotenuse. All I want to solve for is my opposite root. Oh my God, you got yourself what? Trig. We're doing math in AP Chem. No, math is done in all science. Okay, we're doing trig now. No, trig was developed for someone to do what? Solve a problem in science. People forget that. And math is so different. Well, math has actually always been a tool of scientists. It was always created when someone needed to answer a problem. Here's an example of that problem. What is that? So, what do we know? Sine of theta is equal to the opposite over the hypotenuse. Well, in this case, it's the sine of 45, which people know by heart because it's kind of a common one in a right triangle, is equal to the opposite, which is the lattice constant, over 4 times r. What's the r? 0.144 nanometers. And there you go, solve for lattice constant. And make sure that your Kepler is in degrees, because now you're dealing with the unit circle. So 4 times 0.14 nanometers. Okay, it's now you're not multiplying by itself, just timesing by 4, so you can keep it there. Times it by the sine of 45, and you got your lattice constant in nanometers. Okay, making sure I'm in. Forgot how I do to see if I'm in degrees. How do I do that? So, sine of 45, isn't that 0.7 times Can we get a number? Makes any sense? Again, I'm assuming I'm in degrees, and I have to be in degrees, right? Yeah. You can step in and say, no, you got it right. Do I got this right? Oh, mode, right. Mode. I'm in degrees. I'm good. Right? I have to be in degrees, right? Because the unit circle, right? So, yeah, so 0.407, that's it. That's simple. Okay? Did I get it right?
Yes. Right.
Okay. All right. So there's a skill there. All right.